Alright, we want to look at kinetic energy again, but this time when we look at kinetic energy, we want to talk about how much energy a rotating object has. So we said that if an object is moving, like we're pushing a box across the floor, we said that the kinetic energy is 1/2 mv squared. But let's say this time we have some fixed rotation point and we have some object rotating at some omega around this rotation point. Well, this object is moving, but we can't directly just use 1/2 mv squared, because remember that each, like if we're looking at this, let's say this bar, I'm just trying to exaggerate the size, this bar is made up of, you could break this bar into little tiny pieces. And each little tiny piece, what? Is running around a small circular track of varying distances. What we know is we can use our relationship that Ke is 1/2 m, and then we have r squared omega squared. Now, if we have all these little pieces and we want to add up the kinetic energy, we just add up the 1/2 mr squared omega squared for each little block. But what happens then is you can pull the 1/2 m and omega squared out, because those are the same for every single little chunk, because the whole object rotates at the same omega. Then all you have left is the sum of the mr squareds. Now for the given object, for a beam or rotating bound point, the sum of the mr squareds, we said, was I. So what we see is that the kinetic energy for rotation is 1/2 I omega squared. The m's shouldn't come out. I need the m's to stay in there. But the 1/2 omega squared comes out, because we're adding up the different m's at the different r's. So we see that the kinetic energy of rotation is 1/2 I omega squared. And that's the energy of some object rotating in a circle. So what we also need to look at, if that's our kinetic energy of rotation, and this is our kinetic energy of translation, what we need to do is say, okay, what happens if we have some object rolling and translating? Well, then the kinetic energy, because it's translating this way and rotating, you just add it has the energies to both parts of motion. So if you have an object that's translating and rotating, if it's rolling with, without slipping or whatever, however you want to look at that, if you have some object rolling and translating, like rotating and translating, you have both energies. You have both energies of translation and rotation. So this is like your total kinetic energy of your object if it's rotating and translating. Kinetic energy for translation, and we said that as your V goes up, your kinetic energy goes up as a quadratic. The same is true with the rotational. The kinetic energy for rotation goes as a quadratic as well, because omega is squared. All right, so this is just introducing the rotational part of the kinetic energy.